Hello. Today we're going to talk about two priority rules for counting the substituents around a chiral center for determining whether a molecule is more likely dextrorotatory or levorotatory, D or L. This is different than the Kahn-Ingold pre-log priority rule for RNS isomerity. This is not RNS isomerity. It is going to be assumed that you already understand that from somewhere else. This is for finding in a molecular structure whether the compound is more likely dextrorotatory, or it turns plane polarized light clockwise, or levorotatory, it turns plane polarized light counterclockwise. This is to say that if light that has been filtered such that it is only traveling in a wave that is 90 degrees perpendicular through some of these molecules, which way the wave of light will be rotated as it passes through the molecules. The second method that I'm going to discuss isn't official. It is something I figured out all by myself with no help as I was really trying to figure this out. And it's a bit of a work in progress, but it's definitely a general trend that holds consistent across many examples. I found another method on the internet, which I'm going to talk about first, since it's officialized through a source other than me. I had a little help from my shoulder angels on the second method, in which we'll use the infrared absorbance spectra of the substituents. But I don't really see my shoulder angels. I just had to turn my head a lot to really understand what was going on with these molecules. First, we'll talk about a priority rule that is based on the Hammett constant sigma p for each substituent. So, what I have here is a chemistry model set. You don't really need one, but it's useful, especially for teaching. I have a table of infrared absorbance spectra associated with many of these substituents, which we'll use later when we talk about what is, as far as I understand, a Marcus Roizen, that's my name, original trend in D and L configuration. I have a Hammett constant calculator for some of the functional groups that we'll need when we're trying to assign priority to these substituents around a chiral center based on the Hammett constant sigma p priority rule, which I found on the internet, and I will put a link in the description too, so you can check it out and see for yourself. Awesome. On the notepad, we will write sigma p values as we go and do some of our work on paper. Almost all of the examples I'll be working through today are chemical compounds that it is easy to find this data for on the internet already, just for the sake of learning and knowing when we're doing it right. All right, let's get started. I have a very common levo alpha amino acid here that forms proteins along with other levo alpha amino acids in our bodies and in all life on Earth. This is levoalanine. We're going to start by working through the Hammett constant priority rule for this, which is useful for making a pretty good hypothesis about whether a molecule, based off of its molecular structure, will rotate a beam of light coming at it directly vertically, clockwise or counterclockwise. There are still a couple exceptions to this rule, which is why it is only good for making a pretty good guess. There are many cases where it may be necessary to verify this experimentally. It won't be good enough to go off of by itself, but it is a pretty good shortcut for making a prediction about whether or not a specific molecular structure is levorotatory or dextrorotatory. Let's start working through this for L-alanine. First, I am going to write down all of the substituents that we have around the chiral center with a little colon beside that to write down what the Hammett constant sigma p is for that substituent. We have an amine. This is a nitrogen, 2 hydrogens, NH2. NH2. We have a carboxyl, COOH. That's how that is usually written. a methyl group, carbon with 3 hydrogens. And just a hydrogen, which is 0. Very key note. Zero isn't always the lowest priority. Just a mistake I made in the beginning, thinking hydrogen was always lowest priority. I put it in the back, but that was a mistake because a lot of times these substituents have negative Hammett constants, and you're going to want to put the most negative one backwards so you can count the rest. This priority rule generally goes, you number it from 1 to 4 with highest to lowest sigma p-value priority, most positive value first, and then the most negative value last. You put the lowest priority or most negative sigma p group backwards, and then count the rest. If it is clockwise, it's predicted to be dextrorotatory. If it's counterclockwise, it's predicted to be levorotatory. But again, there are a couple exceptions that go their own way. If they have high intramolecular forces, or there's a tie and it doesn't really come out right. But we'll talk about those later. Over here, again, I have my Hammett constant calculator that I found on the internet. I will also put a link for it in the bio, or description rather. I'm new to YouTube. Let's start with the COOH, since I already started on that. Plug that in. You can also just look up a table for this. But it helps to have this when you're looking for a lot of different ones that aren't on every table. 0.523 is the sigma p, which is what we're looking for. It is the most correlated Hammett constant value with optical rotation. There are other Hammett constant values, sigma m, that's at the meta position. The sigma p is at the para position. The Hammett constant is its electron withdrawing or donating capability, which is measured by how the substituent affects the dissociation of benzoic acid when it's substituted around the benzene ring, and the sigma p value is when it's substituted at the para end, which isn't something you need to know for this. Except for understanding which one is going to help you the most. This is for the methyl group, CH3. Got around negative 0.148. NH2. I should have better syntax for that hydrogen. negative 0.57. So it's easy for you to see here. Syntax matters. So, with this, we can definitely assign the NH2 lowest priority. We can assign next lowest priority to the methyl group. Next lowest priority to the hydrogen. And the highest priority to the carboxylic acid. So, we put the amine NH2 in the back. The COOH is priority number 1. Priority number 2 is the hydrogen. Priority number 3 is the CH3 methyl, and then of course priority number 4 in the back. And as we can see here, we've got a counterclockwise rotation here. So we can know that this is levoalanine off of the structure based on that. So I have another levo alpha amino acid here, commonly occurring in proteins, which has many of the same substituents around the chiral center, which I already went ahead and wrote down since we already know these ones. We just have a isobutyl group instead of a methyl group, and I've already plugged that into the sigma p calculator as well, and it is negative 0.142. Very similar. Isobutyl. Then we put the most negative value of sigma p backwards. The group with the most positive sigma p value comes first. Then we number to the most negative. 1, 2, 3, 4. You can just ignore the one in the back. It matters what's in front. 1, 2, 3. Counterclockwise. This is L-leucine. 1, 2, 3, S minus leucine. Minus means levo. Plus means dextro. Now in this example, I have an unidentified enantiomer of 2-bromobutane. And we are going to work through first determining whether it's R or S to put here. Easily enough. You're supposed to know how to do that already. And then whether it is plus or minus here, levo or dextro. You can go ahead and pause the video and try to figure out how to do that yourself if you feel like doing so, or just follow along. This is one that has a close pair of Hammett constants, but they are distinguishable. All right, so we shall begin. We already know the CH3 from up there. We already know the hydrogen is 0. What about the ethyl group that we have off of the chiral center here? Wait for me. All right. That's all I need. I only clicked once and it spit out all that. I just had to turn that into an R group to show that it's attached to something else. Negative 0.17. Significant figures. This is for the ethyl group. Bromo, we'll find that as well. Zero 0.282. So, off of this, we can know to put the ethyl group in the back. We work with what's up front. The bromine will be first. The hydrogen will be second. And the methyl group will be third. So this is going around this way. Counterclockwise. This is minus. Bromobutane. We'll count the R and S isomerity real quick. We've got the highest atomic number here, 1, 2, 3, 4. Of course, hydrogen's in the back. So clockwise, it's R minus bromobutane. I'll do one more worked example of using the Hammett constant sigma p priority rule for making a fairly accurate hypothesis at whether a molecule is levorotatory or dextrorotatory just off of its structure. And as a reminder, when Hammett constants are very close to each other, as with the last example, this often gets confusing, and it can be the other way. So it's a good idea to either have a tiebreaker, like the trends that I discovered following a very consistent pattern with levorotatory and dextrorotatory molecules that I'll be teaching at the end to break the tie or double check that it's right, or to wait until you have experimental data on the compound to see whether it actually turns plane polarized light clockwise or counterclockwise, which will always still be there to be sure. So, an unidentified enantiomer of 1 amino propan 2-ol. We already know the Hammett constant of the methyl substituent and the hydrogen. We just need to find the OH and the amino methylene, I think, NH2CH2. So I already have that plugged in here. It's negative 0.096. This is pretty close, but the article on this said around 0.05 is the cutoff for too close to tell what the sigma p priority rule. So we'll go ahead anyway. And we need to find out the Hammett constant of the alcohol. Is negative 0.325. So we have hydrogen, highest priority, the OH, lowest priority. And if we, actually let's do RNS first just to go in order. We're trying to figure out whether it's RS plus or minus levo and dextra. So count RS. 1, 2, 3, this is S. Then we'll turn it back around where we left off. OH goes last. Hydrogen goes first. This is the CH2NH2, negative 0.096. It comes before the methyl. 1, 2, 3. This is S plus. Or dextro. One amino propan 2. Now we'll move on to exceptions to this rule. Now we'll talk about examples of chemical structures that the Hammett constant sigma p priority rule will not work on. I'll be working through two examples. Then I'll mention some others. One was mentioned in the article, and it was the protonated form of L-phenylalanine. Then I'll also mention that a lot of times two carbon chain substituents, in my experience, have Hammett constants that are too close to each other to work with the Hammett constant sigma p priority rule alone. Anyways, penicillamine we have here. We already know NH2 has negative 5.7, COOH has 0.523, H has 0. We just don't know this thiol isopropyl thing. I already have it plugged in here. Sigma p 0.025. Write it down. So the amine goes last, following the rule. Carboxyl will come first. Hydrogen, or rather the thiol isopropyl will come second. Hydrogen will go last. And that's a minus rotation when this 1, 2, 3 S isomer is supposed to have a plus rotation. We'll talk about how I can begin to make sense of how it goes with this one in terms of interaction with the energies of light with my way when we get to that one, but there's no way to make it work with the Hammett constant sigma p priority rule for penicillamine, which is not penicillin, it's penicillamine. L plus lactic acid. I should also mention that this has nothing to do with the naming of compounds that are related to glyceraldehyde, because those ones are just named after the enantiomer of glyceraldehyde that has the first OH pointing in the same direction, which is why a lot of those ones are named differently than their optical rotation actually is. Sugars, lactic acid, a lot of times you'll see this L plus, and that just means that it's more related to L-glyceraldehyde and it has a plus rotation. But we see again with all of these that we know already that the Hammett constant sigma p priority rule doesn't do us any justice here, and I can't figure it out with the infrared absorbance either. This is one of those ones that just flips around differently than we can understand. The article said it was because of its interactions with water. If we count in order from here, 1, 2, 3, we get a minus rotation. Don't be confused by the L. Remember, that's related to L-glyceraldehyde, and this is supposed to have a plus rotation. This is the S isomer. 1, 2, 3, S isomer. It is supposed to have a plus 2.6 degree rotation of plane polarized light. It would rotate plane polarized light 2.6 degrees. And there's just no way to make it work with either of the trends I know. There's no way to make sense of lactic acid except to realize that, you've got intramolecular forces here. I guess it would have been dissolved in water when shining light through it, and that would have caused some differences in how these groups withheld electrons. And this is an outlier with penicillamine, a protonated form of phenylalanine. Molecules with substituents that are too similar to each other. But with a lot of those molecules that have substituents that are too similar to each other, I can break the tie with the infrared absorbance of each substituent, which correlates with the infrared reflectance of each substituent. Where there is not absorbance, there is reflectance, and we want the highest potential change for a photon that's going to reflect off as many of these as it does, but the biggest potential difference in that will be the biggest factor determining which way it turns the light, and that's what we'll be talking about with the infrared absorbance priority rule preliminary. Marcus was an original consistent trend. It's as, if not more consistent than the Hammett constant priority rule in my experience. Now I'm going to explain the method that I figured out myself with no help that works 98% of the time, approximately, that I just stumbled upon with a determination to figure it out, fully believing that there would have to be some sort of order that they could be counted with, like the Kahn-Ingold pre-log rule, assigning RNS isomerity just different and for determining whether the molecule is levo or dextro off of the molecular structure. I firmly believed that this had to exist because if you flip the RNS isomerity, it always flips the L&D isomerity. There's an order to RNS, and if you switch that, it always switches the L&D from what it was. So there had to be some order around the chiral center that logically fit the switch, because if you just switch one of them, always it switches both the RNS and the L&D, so there would have to be an order for that as well. I started by I started by realizing what was given already. We know that L&D isomerity is the enantiomer's ability to rotate a wave of light that is traveling at 90 degrees vertical into the substance, clockwise or counterclockwise. So then I thought, what do we know about how these substituents interact with light? And I thought of infrared absorbance. I still have my class activity handout from when I learned this in Organic Chemistry 1, which is what I'm going off of here. And I didn't know how generalizable infrared absorbance would be with rotating plane polarized light, but I decided to try to figure out a pattern with that anyway, and it seems to me that it has a lot to do with starting with if possible, starting with the side that allows the light, the most light to enter in the first place. Like this is really obtrusive, so you wouldn't start with this because the lights, if the wave of light were to travel directly down this, most of it would get absorbed, or maybe not most, but a lot of it would, and that would be less significant than paying attention to the light that enters where most of the light is going to enter, the least obtrusive side of the molecule. Which only seemed logical. It comes down this way, not very much of the light is going to get through, and it doesn't really matter what bounces off or how it bounces off. If it goes in that way, it made more sense to pay attention to where most of the light is going to enter from and where it's going to bounce off. And the lowest energy infrared absorbance means the most higher energy or the biggest area under the curve of higher energy reflectance possible. And you know, I thought photons lose a little energy every time they reflect. We want how, you know, how most of the light that makes it through the molecule is going to turn based on how it reflects off of each one of these. And it made the most sense to try to start with the side that would let the most light in, and then count from lowest energy infrared absorbance without any higher energy absorbance obstructing that way. So you disqualify anything that has major higher energy absorbance, and you prioritize that last. It's kind of a prioritizing last thing. You prioritize the highest energy absorbance last, and then start with the lowest energy absorbance. So we have this here, you know, these two would be a tie if we started counting around this, and these are pretty close anyway. So we wouldn't start with the first bonds out from the chiral center. So we move on to the next bonds out. These are lower energy absorbance than these. Carbon, hydrogen, sp3 bonds. I estimated these ones to be a little bit higher than these ones because they have a higher, they have, or rather I meant higher priority. They have a higher priority. They have a lower energy bend absorbance, and they're in the same range estimated stretch absorbance, but oftentimes the bend absorbance kind of falls in the same side of the stretch absorbance, and these have a little bit lower energy bend absorbance, which means they probably have a little lower energy stretch absorbance, which means they're higher priority because they reflect more high energy light coming through, losing energy off of each thing, and coming out the other side a little bit rotated. So I decided to prioritize these first over these. Goes from here to here to here. We're looking at 2-aminopentane. This would be a plus rotation. I like to make that sound to conceptualize this. That is a plus rotation. We'll write that down real quick. We have plus 2-aminopentane here, or dextro 2-aminopentane here, since they're going clockwise around this. Not much we can do here. A lot of ties or almost ties here. It bounces off this at the highest energy light that's gonna get lost less easily. Bounces off here, bounces off here, bounces off here, goes out this way. So that's NH2 over CH2 over CH3. We kind of omitted the single hydrogen here just because it, you know, it's not as relevant to how we assign things being, you know, with these ties. It'll bounce off this, kind of probably go to this. There's not as sure of a way to do that, and there's a bigger difference here. It's not even going to matter here. So we have plus 2-aminopentane. It is 1, 2, 3, S. I had an example. Basically what we have here, it's R minus. We had 1, 2, 3, S plus. If it's R minus, that means that S plus is correct. I'll have another example ready in just 1 second. So for this example, an unidentified enantiomer of 2-butanol or butan-2-ol, TU. I am going to introduce how the Hammett constant sigma p priority rule can fail, and where this can help resolve the lack of clarity. We have a chiral center, 4 substituents, 1 being hydrogen. I'm also going to talk about how I have been able to use this way for chiral centers that have all non-hydrogen substituents. Non-carbon chiral centers are something that I have yet to fully explore, and this is not for that yet, at least. I don't know if it doesn't work, but I don't know if it does work, so we're not going to talk about that yet. 2-butanol. It is 1, 2, 3 R-butanol. Now, using the Hammett constant priority rule, we put the OH in the back. And then count from most positive to most negative, so that's going to be the 0 hydrogen, to the methyl, CH3, negative 0.148, to the ethyl, to the chiral center, this C2H5 ethyl, at negative 0.17. And that's actually going to be wrong, because these two are too close to each other, and it just doesn't work out that way. So using our little heuristic with the infrared absorbance, remember that a larger wavelength means a lower energy. I'd have expected you to know that before you really get to here, but I'll remind you of that anyway. We're going to get a lot of ties with these first bonds out, especially since we have two definite ties. But we come out to here, second bond's out, and we have some ones we can distinguish between. This is definitely highest priority, lowest energy absorbance. It leaves a huge area under the curve of higher energy reflectance unobstructed. We want what the waves coming out of the molecule. We want what is going to have the biggest effect on the waves that make it all the way through this molecular structure with a rotated wave. So we start with the largest area under the curve of higher energy reflectance, or just the energy absorbance. Then we work our way around to the substituents with less area under the curve, higher energy reflectance, which would just be a bit higher energy absorbance range, which is actually going to be this way, because these ones definitely have a little bit lower energy absorbance than these CH3s over CH2s, or it's the carbon hydrogen bond of the CH2 that's a little bit lower energy than the carbon hydrogen bond of the CH3s. So it comes around this way, bounces off here, exits there. It clearly rotated in a counterclockwise direction, gives us minus. R minus butan 2-ol, or R minus 2-butanol, which is what I have here. Voila. Now I have an example of a molecule with a chiral center that has all non-hydrogen substituents on the chiral center itself. These are all alkyl chains, carbon hydrogen chains, or a methyl group. And when I first tried to figure this out, I thought, the these are all a tie, clearly, the first bond out. And the least obstructive side of this would probably be the side of the methyl group, which doesn't work. You have this facing forward, you can't, you know, there are more CH2s along this one, this one, this one. 1, 2, 3. This is, it'd have to be plus. Plus 4-ethyl, 4-methyl octane. And it's actually the other way around. So I kept thinking about what it could be, and I realized that it doesn't really matter which side is the least obtrusive at this point, because they're all pretty much equally obtrusive when it comes down to getting into the chiral center. So I prioritized them again based on my infrared absorbance priority rule. Largest wavelength first, lowest energy absorbance first, meaning the largest area under the curve of higher energy reflectance left, because where there is absorbance, there is not reflectance. Where there is no absorbance, there is reflectance. We want the largest area under the curve of higher energy reflectance first, because that's what the photons will start out with. They'll lose energy as they go around the jungle gym, and then they'll bounce off the least high energy reflectance last. When they're at their lowest energy, they lose energy off of each one of these. They go out at their lowest energy. The color of light changes. We know that, the barber pole effect. And then that's just the way it goes. So highest energy here. Next is here. Or highest energy, the most high energy reflectance here. A lot of that. Next is here. Next is here. Last is the methyl group. 4, 3, 2, 1. And minus. That's going the right way. Doing a plus rotation here. That's going the right way. And you know that makes perfect sense. The light can get in equally at all of these angles, and the biggest change that it can undergo throughout all of these substituents is from the largest area under the curve of higher energy reflectance to the lowest area under the curve of higher energy reflectance. That is the biggest change it can undergo. Some of the light will. That is what's going to matter most. It's going to turn counterclockwise because of it, and that is what this is. 1, 2, 3, 4. This is R R minus, wait, 1, 2, 3, this is S, I meant S. S minus 4-ethyl 4-methyl octane. Go ahead and look that up on your own. Now that I've introduced my original idea of the trend I noticed with the area under the curve of higher energy infrared reflectance, I am going to start showing you how I kind of put the two methods together to be as sure as possible. This is, you know, it's the dextrorotation isomer. 1, 2, 3. This is S plus hydrotropic acid. I already wrote down Hammett constants here, sigma p values. I got some of them from the article. And then I wrote down already the priorities I would assign with each method. And to show you what that is, it is we'll do the sigma p first. Methyl group faces backwards. This goes one, 2, 3. See, you got a clockwise rotation here on through. So it's dextrorotatory by the sigma p rule. Let's go through infrared priority. Hydrogen forward. I just put hydrogen as priority forward because it lets a lot of light into the rest of them. And it will bounce off from the methyl group to the COOH, because this has a little bit, higher energy than this. This has a little bit more higher energy reflectance. More higher, yeah, that's actually proper grammar. More higher energy reflectance. And same deal here too, with these two. If you're looking 2 and 3 bonds out. So it goes here to here to here, and then on out that way, which is clockwise and thus dextrorotatory and positive, like we were looking for. And these might have needed a tiebreaker too. All right, I know I said we were going to do a mystery example, But this video is getting long and you've got plenty to get the idea anyway. So I'm gonna stop it there. Thank you for watching and learning and spreading the knowledge about something I find very exciting. I probably won't do very many YouTube videos on this YouTube channel. If I do, it will be many different subjects in more depth as I find things that I delve deeper into, because I'm that sort of guy. I could teach you how to make a fish tank that doesn't require any water changed in it. It just runs on its own ecosystem. That's a hobby of mine. I just have this magnet scrubber here to get rid of algae on the side of the glass. Use it whenever I need to, but I don't feel a need always. It's actually healthy for the aquarium. I sing. I love a lot of math and science. And 4-letter personality depth psychology. I also have delved quite a bit into that. And I could teach that as well in some pretty well synthesized points, key points. They're not all mine at all. Everyone can have original ideas on that.